All right, everyone. How are we doing today? I apologize for the delay getting started here. New room, and of course, I had two or three of the things that I was trying to set up here not work right away, which they should have. Anyway, um, for those of you out there on the internet, we changed classrooms. We're in a bigger space, which is nice. Not quite as cramped. I know you have a little bit less table space because you have desks or little like individual desks instead of that, but my situation has improved, which I'm very happy about. I don't have to worry about my attachments that I plug all my gear into falling off the table, which is very nice. But anyway, I'm glad we all found the spot and that the change, I guess, was okay. I think I'm not sure if in-person attendance has lowered a little bit just because we're a couple weeks in and people are adjusting to stuff or how that's going, but we'll be all right. Okay, so today we're going to start talking about chapter 13. Okay, um, chapter 13 is about vector functions, which we've had a little bit of exposure to, but we're going to go deeper into today. And I also do want to mention, since we're starting chapter 13, that our first exam isn't terribly far away. We cover one section from chapter 13 this week, and then I think there's only 3 more sections left in chapter 13. It's a relatively short chapter. Okay, so do check the schedules and make sure that you're getting ready for that. And then we'll have a little bit of review time before the exam too, but that is coming up fairly soon. Okay. We have a function, and we call it vector valued if it maps to more than one variable, or if they map to a vector. Okay, so an example of some vector valued function would be, say, your book tends to use the letter R here. If we had a function that mapped from one variable to 3 variables. So the idea of the composition of this function would be something that looks like this, where the way that the function is set up is that we have the vector function, which is R, and then we have these, which are called component functions. Okay. And for these component functions, they are functions in the sense that you are used to thinking about them. They're one-dimensional functions, and they map the real numbers onto the real numbers. Okay. Or sorry, map the real numbers into the real numbers. I have to be careful about using the word onto. Okay. So F, G, and H, stuff you're used to working with. All right. And then basically we just grab a collection of them and work with them all at the same time as one example of a vector valued function. Okay. Now, it would be perfectly within bounds to have a function that maps Rm to Rn. Okay. This would be an example of a vector function as well because it maps to a vector. But dealing with stuff like this is going to be, we're going to be dealing with some limited cases of this, and it's more the domain of linear algebra. Okay, looking at things that do that. It is particularly nice if we can represent that sort of thing as a matrix. Okay. So as is an example of what we're looking at here, we can choose the following component functions. As a starting place, and then think about what our vector valued function might look like. So when we write down the formula for a function, what's one of the things that we have to worry about? What do I need to understand about a function in order to really know how to plot it and how it works? And you know its dimensions, all right? That's something that we can get from the context of the problem. Okay, for us, we have one independent variable mapping into 3 dependent variables. Okay, so t to x, y, z would be another way to think about it. Okay, where we think of x, y, and z all as functions that depend on t. It's kind of another way of writing this, right? Okay, now that's one thing we need to know, but let's just isolate this function here. Okay, what do I know about the function g of t? The radicand is not allowed to be negative, right? What do I know about this function? What kinds of numbers am I not allowed to take the natural log of? Non-negative numbers, right? Or non-positive numbers, all right? Natural log of 0 is bad. Natural log of negative numbers is bad, okay? Both of those things represent domain restrictions for the function, right? And a lot of times we're fairly lazy as people who are writing down mathematics and don't specify all the time the domain restriction unless we're giving you the domain restriction on top of other information about the function, right? So here, I don't tell you that these things aren't defined for all t, but the assumption is that you can look at it and know that there are t's that aren't allowed, okay? But if we don't otherwise specify some kind of domain restriction, we work under the assumption that it's all t's that are okay, right? Like if I don't give you a domain restriction on the sine function, you assume that it's defined for all real numbers, okay? This one is defined for values of t that are greater than 2, greater than or equal to 2. Sorry, less than or equal to 2. And this is defined for values of t that are greater than 0. Okay, so this comes with the domain restriction, and this comes with the domain restriction. Which imply a domain restriction on the vector function. It has to satisfy both of those conditions, right? The square root of 0 is okay. Yeah, no, the minus sign messes it up. I know. I made the mistake when I was saying it out loud a minute ago. Okay, but so that gives us a domain restriction on R that looks like this. Okay, or we can write it in interval notation if we want. Okay, so something to be on the lookout for. All right, there are more functions being thrown at you. Okay, there's a larger temptation to skip that step because it's just more of a hassle. All right, but one of the things that you have to train yourself to do and stay in practice about is when you evaluate these vector functions to make sure that you double check what's the domain of this thing. All right. There are going to be situations where it's given to you, which is really nice. There's going to be situations where it's not. You have to make sure you're checking. Okay. Because this one was picked because its domain's pretty small, right? So keep an eye on that. Okay. But the nice thing about it is that our component functions are more or less independent. All right. A lot of the workings for the mathematics behind this allow us just to deal with the component functions on a one-by-one basis. We deal with them one at a time and don't have a lot of extra nonsense going on. Okay. This, fortunately for us, extends to limits and continuity. All right. So back in Calc 1, one of the things that you should have talked about is the epsilon delta definition of a limit, right? And it says, sorry. We say for each, oops, goodness, we say that the limit of x approaches x naught of f of x equals L if for each epsilon greater than 0, there is a delta greater than 0 such that if the distance between x and x naught is less than delta, then the distance between f evaluated at x and the limit is less than epsilon. Okay. So this was the definition for one dimension. Okay. And it turns out that there isn't much to change if we want to talk about this. I'll just use x. If we want to talk about this in terms of vectors. Okay, so I wrote x here. It's the same thing as t in the way that I used it before. It's just the independent variable. It's a scalar. Okay, so for 3D, basically it works the same. Okay, we specify an epsilon. The epsilon represents the way that I think about this is that epsilon is an error bound. Okay, epsilon is a value that tells me how close to the answer that I have to be if I'm evaluating a limit. Okay, The delta is an input precision. Okay, so I'll write that down. And the way that the definition of a limit works is if you give me an error bound, I can tell you what the input precision has to be in order to make sure that the function is within that error bound. Okay? So if you tell me that I have to be epsilon close to the answer, I can tell you that if you're within delta of this input, then you're going to be within epsilon of the answer that you asked for. Okay? And the idea is that if for every error bound there is a corresponding input precision that works, the limit exists. Okay, because they both vanish as epsilon goes to 0. Okay. In 2D, the picture looks something like this. You have our limit, and if you specify an epsilon, so you have x plus epsilon and x minus epsilon, then you'll get a delta that traps it in that box. Okay. So this is L plus delta. Sorry. Yeah. Sorry, this is L plus epsilon and L minus epsilon. I said it backwards before, I apologize. Okay. That's what it looks like in 2D. In a 3D, we have some curve, okay? And what I'm interested in is what the function looks like at this value, right? Okay. Now, the way that the input value works for the curve is that I have to imagine that I'm traveling along the curve, right? That's what varying x does, or varying t, whatever the parameter is for my curve. Okay, so the value for, if I say that x or t minus t naught has to be less than delta, or x minus x naught has to be less than delta, what I'm specifying is that it's within some interval, right? And the epsilon part becomes a sphere, or an epsilon ball is how it's usually referred to, that the function has to be within. Okay, so you specify the radius of a sphere that the answer has to end up in, and then I have to tell you how small delta is in order to make sure that the function is there. And if for every epsilon there is a corresponding delta, the limit exists. Okay, it's basically the same thing. Here I have a one-dimensional ball. It's just an interval, right? Here I have a three-dimensional ball, and it's a sphere. Okay, in 2D it's a circle, and you end up with hyperspheres if you exceed 3 dimensions. Okay, but this is the basic principle behind how it works. Okay, is this helping people put together some stuff from Calc 1? Maybe, we hope. Yes. Yes, that's correct. The question, for those of you on the internet, is epsilon is how close you have to be to the answer. Okay, so epsilon is associated with the value of the vector function. Delta is associated with the inputs. So epsilon is how close do I have to be to the answer in order for the limit to make sense. And delta is how close do my inputs have to be to the point where I'm finding the limit at, because it's the limit as x approaches x naught, or t approaches t naught. And that's the one that delta goes with. Okay. So this is what the limit picture looks like in 3D. And for the purposes of computing this, we kind of catch a break. If we want to know what the limit of a vector valued function is equal to, we, and I would imagine some of you would describe this as mercifully, get to do this component-wise. Okay? So, from a practical perspective, we don't, like we didn't in Calc 1, think about limits very often in terms of the epsilon delta sense, but if we're doing things with the definition, then that's how we have to work with it. But for practical purposes, since we know how to compute 1D limits, we can do vector valued limits in this sense by examining them component-wise. Okay. Okay. Now, because limits work the same way in the vector valued case as they do for the individual cases, if you know that the component functions are continuous, you can use that to help you evaluate the limit. Okay. And of course, we know from Calc 1, the definition of continuity is a function evaluated at a point is equal to its limit as it approaches that point. Okay. So function's continuous, you need to evaluate the limit there, plug in the number. And then if you're computing limits, you also can use whichever tricks you may or may not remember about your 1D limits. Okay. There's a couple of exercises to check out in the textbook and then on the online notes page. So please make sure you take a look at those. Okay. All right. With this understanding of vector functions, we can also talk about what are referred to as parametric functions. And the idea is that we also call these space curves. We make the association that I hinted at earlier where we have x, y, and z associated with these component functions, and use this to construct collections of ordered triples, and these collections of ordered triples form our space curve. Okay, so the idea is that t is going to be in some interval. Okay, and then we allow t to increase from the left part of the interval to the right part of the interval, and then the set of all ordered triples that we generate by allowing t to move through The set of values in the interval gives us a collection of ordered triples, and that collection of ordered triples is the space curve. Okay, so drawing the picture, we would have some situation, right? And this would be the minimal value in the interval, and this would be the maximal value in the interval. We get some curve. Okay. There aren't any rules that say that the curve can't self-intersect or trace over itself or things like that. Okay. We call these vector functions because each of the components have to be a function. Okay. But the graph that we're looking at may not look like a function in the sense that you're used to. Okay. So I think we had part of this discussion earlier this week. Okay. We have to remember that this thing is four-dimensional. Okay. There's one input dimension and three output dimensions. So the information that's being represented here on screen is not complete. All right. All right. So as an example of what one of these things looks like, we have example 2 here on the screen. Okay. This is an example parametric function, example space curve. We can write this out as letting r be a vector valued function that's equal to sine pi t I minus cosine pi t j plus cosine pi t k, or I hat, j hat, k hat, however you'd like to say that. I could have used the angle bracket notation to write the components. Either way is fine. You're going to see both, so both are going to show up. And for this space curve, looking at it, you have to realize that it's drawn in perspective, right? Okay, so it looks like it's an ellipse, but if you look at the equations for I and j, that looks awfully circular, right? Okay, so if you looked at it from directly above, it would look like a circle. It's just tilted in perspective because of what's going on with the z value. Okay, and then there are a couple of important features of this that we need to keep in mind for whenever we're drawing space curves, and that is the curve has an orientation to it, which is given by these arrows here. Okay, and then because these functions are all periodic, this curve would be one that if we allow t to increase, is just going to keep tracing over itself. Okay, and the way that we would draw the function is we think about r as a vector from the origin whose arrow ends up at some point in space. Okay, so the curve is drawn by where the tip of the magenta colored arrow traces out. All right. Questions about this? Seems okay. All right. The real test here, of course, is to do some examples with these and get an idea of what these all look like, right? Okay. All right. Now, the other short example here is that we want to make sure that we are remembering our knowledge about equations of lines and equations of planes, because they can also be thought of in a vector sense as well. Okay. So the short example here is an equation of a line that has this vector form. Okay. And then another notational thing that we can take a look at are plane curves. Okay. There isn't anything stopping us from writing a two-dimensional equation that looks like this. Seems fine, right? Okay. And the idea is that we could also write this like so. Where in this problem, I and j are the two-dimensional versions, and we could have this curve here. Okay. If I wanted to plot this, I'd need a little bit more careful because we're used to thinking of our two-dimensional plots as looking like this, right? Okay. Now, the difference here, of course, is that this is a parameterized function, so I drew a 2D picture, but it's really a 3D graph, right? Because you have one variable for the input t, and then x and y are both outputs. Okay? So like the parametric equations and the space curves for this form, there's a hidden variable, right? There's the variable that I am traversing along the curve. Okay, that's where t goes. And then the spatial values go along with x and y. Okay? And then a little tricky to sketch this, but we can cheat. All right. So, have I used Desmos this semester in this class yet? Okay. All right. This site is called Desmos. That's the name. If you type that into a web search engine, you will find this. This is their calculator feature. I happen to like this website a lot. For this class, I can't use it quite as much because this is way better at doing two-dimensional stuff than it is at doing 3D stuff. But we can use it for the example that we were just discussing. Okay. So what we can do for this is we can give ourselves a helping hand here in order to graph the parametric function that we had written on the other screen, t squared, and then t minus 1. We see that it only draws a partial part of the curve because it wants us to specify a range of t values, and we can do that. And so we get these numbers here. 5 is a little big, so we'll change the cutoff and make it smaller so we can see that it does indeed terminate. Okay. So we get our values here. Okay. If we had a more complex expression, it could also show us what's going on with that. Okay. And if we want to get really fancy, you can define variables by just typing in a letter that isn't used somewhere else. Avoid X, Y, T, and R because sometimes those are reserved for other things. E is also something you want to avoid. But other letters, A, B, C, or capital letters should be fine. And what we can do is we can say that we want this to go from -3 to, say, I don't know, 5. Okay, and then we can use the slider and actually draw the curve this way to get an idea of what the orientation looks like. Okay, so if you're having a little bit of trouble picturing one of these things, you can do this. All right, to get the parametric curve stuff, all I did was just use a set of parentheses and start typing a formula. Another way that I could have done this, by the way, is say f of t equals t squared, and then g of t equals e to the t, and then up here, this can be f of t g of t. So if I have complicated expressions that I want to be on their own lines, or if I want to look at their graphs independently, I can see all this different stuff. Okay. All right. No questions in the chat? Okay. For plane curves, for the other axes, if we want to think about it in terms of just like a projection in 3D, we can, like we did with traces in 12.6, just set one of the coordinates equal to 0, right? So if I have something that looks like r, where I have t and t squared, what I can do is I can figure out what the projection of the curve looks like on the xy plane by setting z equal to 0, on the xz plane by setting y equal to 0, and on the yz plane by setting x equal to 0. Okay, and then we can use those projections in order to help us get an idea of what the overall curve looks like by synthesizing those sketches. Okay, and there's an example that's here on the page that you can check out later on. Okay. The other way that we sometimes define our plane curves is by using intersecting surfaces. Okay, so for an intersecting surface, the idea is that we're given a couple of equations. Say, and this is in 3D, of course, we have x squared plus y squared equals 4, which is a circular cylinder of radius 2 that's vertical. Okay, and then we can also have a parabolic cylinder. Okay, cylinder, by the way, in 3D means some static shape that is copied for every height or everywhere along a line, right? So for a cylinder, we know that it looks like this. Okay, and then it obviously extends forever in both directions, but we tend to truncate it just so the picture is manageable. Okay. Clean this up a little bit. All right. And then for the other picture, we have z equals x squared. And the way that this works is that it should remind us of a parabola, right? Okay, we know what the graph y equals x squared looks like. Okay, we're used to drawing that picture. All right, z equals x squared, same sort of deal, right? So we have to draw this in perspective because it's along the z-axis, right? And so this gets copied for every height. Okay, so there's a parabola shape, but it's going sideways relative to the screen. Does that make sense? Sort of. Maybe if I draw one picture, it'll look a little bit better. Like that. Sorry, I'm not an artist, so I have to think really hard about this. That's why I use the toys. Okay, so, and again, the point is that this is the xz plane, right? So this is the one that the parabola is in. That's why it goes sideways. Okay. What happens is that we want the surface just defined by the intersection of these two things. Okay. And it's hard to get an idea about until you see kind of everything put together. But the curve ends up looking something like this. Kind of a wobbly thing where the sides of the parabola hit the cylinder. Okay, but there is a top point to it, and then the intersection. You end up with a closed curve. Okay. So on the notes page, in order to help everyone out here, we can parameterize the equation, okay, because parameterizing the equation of a cylinder is easy, right? We just use sines and cosines. And then from there, it's really easy to figure out the parameterization for z because we know what x has to look like. So we just plug it in. Okay. I linked to a different website here that is the one that I used to generate this figure. Okay. And I think that the link should take you to what I actually typed in. So you can copy that in the same way that you can copy what I would have typed into Desmos in order to get a 3D picture. And in this case, it looks like this. Okay. And what I did below here was graph the component surfaces to try to give you an impression of what these things look like together. The drawing both surfaces on top of each other, trying to do the intersection would just look gross. It wasn't helpful. That's why I kept everything separate in this version. But I think this makes a little bit more clear why you get kind of this wobbly curve. Okay, because if you just imagine taking the parabola and using it to slice through the cylinder, and then you pull the top part of the cylinder off, that's what you would have left. Okay? Alrighty. So what do we think? Seems okay? This one is definitely more of a technology aided situation. Or no, that doesn't mean that you shouldn't try to understand how to work with these things. The analytical skill is being able to do the parameterization. I realize that in the live discussion I glossed over that a little bit, but make sure that you take a little bit of time, read through that, and then go through the examples in the text. They have some different things that they did with the visualizations that they generated. So just flip through those, and the kind of the overall arc for this past week is you need to make sure that you can start drawing the connections between what parameterized equations and vector functions look like and the associated surfaces and space curves. Okay, look at that, start to develop that intuition, and then start training your brain to be able to understand that geometry. Because what we're going to have to do moving forward is be able to look at a region in space and come up with a way to parameterize it. Okay, and we're going to need that parameterization to help us do things like compute integrals. Is going to be kind of the ultimate goal. All right. So you need to make sure that you understand the lines and the shapes and the geometric relationships so that you can process that into an analytical statement and then be able to do calculus to the analytical statement. Okay? Take care, everybody. Enjoy your weekend, and I will see you next time.